So this video we're going to go over the mechanism of the Pinacol-Pinacolone rearrangement. So the Pinacol-Pinacolone rearrangement starts with a diol. I'll use a very simple example of a diol. So it's a 1,2 diol where the alcohols are on adjacent carbons to each other. All right, and we're going to react this with acid, and the product of this is going to be the ketone. So right away, let's look at the bonds that have been broken. We definitely break one of the carbon-oxygen bonds. And we've also lost one of the methyl groups here. This one has shifted over. It's not attached to this carbon anymore. If we count these 1, 2, 3, 4, 1, 2, 3, let's call this 4, we've obviously lost that group. And the bonds that are formed from this, we form the double bond. And I missed one breaking bond here. We actually break the hydrogen-oxygen bond of this. So that's one thing that gets lost. And the other formed bond is one of the methyl groups that shifted over to carbon 3. There were 2. Now there's 3 that are attached. Okay, so what goes on in this reaction? Just like any reaction of an alcohol, we're going to start out simply by protonating the alcohol. The alcohol has extra electrons. It reacts with H+. So this is the nucleophile. It does the attacking. The H+ is the electrophile. It gets attacked. And that attack happens simply like this. And we're going to draw the product of that. So what we're doing is creating a bond between the oxygen and the hydrogen. So what this looks like now is it kind of looks like water. We're getting ready to eliminate water from this reaction. So we're going to do that. We're going to break the bond. So I'll take the 2 electrons from the center of the bond and put them on as a lone pair on the oxygen that will eventually become water. By breaking this bond, taking the 2 electrons that are in this bond away and giving them the oxygen, I create a positive charge. And what we wind up with is this carbocation. All right, so this is a tertiary carbocation, and it's a relatively stable carbocation, but I have an oxygen on the adjacent carbon. And what could happen with this oxygen, if the plus charge was on this carbon, that oxygen could help stabilize it. So what happens is, even though this is a stable tertiary carbocation, I get a 1,2 alkyl shift. Right, so let's just say this is protonation, and this is loss of water, and this will be a 1,2 alkyl shift, and what I get from that is the alcohol where the plus charge is on the same carbon that the oxygen has. Now, because of resonance, this is a stable carbocation. These electrons could come in here to satisfy the plus charge. And I'm going to draw this as a resonance arrow because these are resonance structures of each other. So I'll get this protonated molecule here. And then I need to do a loss of the H+ to give those back to the oxygen. And I wind up with H3O+. So I get my acid catalyst back in this reaction. Okay, if we were to do this reaction on a molecule that contains a ring, the 1,2 migration becomes a little special now. Okay, so let's see what happens here. So H plus, we'll start this just like any other. We'll do the protonation. We'll get something that looks a lot like water and is ready to be eliminated. And we'll do that elimination of the water. And what I wind up with is this alcohol and this carbocation. Okay, so again, being next to the oxygen for that carbocation would be better. But now the alkyl migration, it's not as simple as it was before. Instead of moving a group, I'm actually moving the ring, right? So if I start counting, let's do this in blue. 1, 2, 3, 4, 5. We'll call this 6, 7, 8, 9, and 10. What I'm doing when I move that alkyl group over, I'm forming a bond between carbon 5 and carbon 6 when I do that. And I'm breaking the bond between carbon 1 and 5. So that bond is getting broken and I'm shifting it over. So I'm forming a bond between 5 and 6. And let's just write that in with a lighter color. This is the bond that I'm creating. All right? So what that is I have a 6-membered ring now. 1, 2, 3, 4, 5, and 6. And we can draw that as the 6-membered ring. So if this is 1, 2, 3, 4, 5, and 6, when I do that transfer, so 1 has the OH, so let's draw that on. I've broken the bond between 5 and 1, so that leaves a plus charge at 1, because I've moved that over. And now if I look at the connection, that carbon between 5 and 6, carbon 6 has carbon 7 and 10 on it, right? This and this are part of carbon 6. And when I do that shift, what I get is that 5-membered ring that's fused on just like this. And again, resonance stability. I'll draw this as a resonance arrow. What I'm going to get is the carbonyl that's protonated and the 5-membered ring hanging off of it. And again, I'm going to do a loss of that proton. And what you wind up with is the ring expanded compound. So one of those rings goes from being a 5-membered ring to a 6-membered ring.